Welcome back to this session on the buck converter that we've been analyzing so far. This session we are going to take a look at an example. We are going to look at an example of the buck converter with some parameters given where we need to calculate some parameters. So we've taken a look at analysis. We've looked at various equations which characterize the buck converter, and we need to take an example. Before we actually take this example, I just want to give a very brief overview of what we've learned so far, and in the form of the various currents which flows through the various elements in the buck converter. So what are the elements? We have the source, we have our switch, which is basically in series with the source, we have the diode, we have the inductor, we have the capacitor, and we have our load. You should be able to sketch the various current waveforms which goes through each of these individual components. Now, in addition to being able to sketch them, you should be able to find the average values, you should be able to find the RMS values of these waveforms. So we are going to take a very quick overview of these waveforms, and then we'll come back to the example. So I'm going to go up to an open page where I try to sketch some few currents. So on this page I just put some few waveforms of the current, and you are going to help me find which of these currents belongs to which of the elements that we have in the buck converter, and I'm briefly going to go over. So when you look at this, I think everybody should be able to figure out what this current waveform is. So you are going to know that this is the current IL. This is the current waveform through the inductor. So when the switch is closed, the current in the inductor increases in the first period, and then when the switch is open, the current decreases in that period. So the first waveform over here we know is going to be for IL. The second waveform I have over here, if you look very closely, we have the current going up. So the current is the same as that of the inductor, but then when the switch is closed, when the switch is open, which is the next half cycle, the current goes to zero. Now, which of the elements in the buck converter do you think is going to match this? And this is basically the source. So this is IS, or the switch. Okay, so this is the current from the source, or the current which is going through the switch. They are the same as the inductor, but then when the switch opens, that current goes to zero. If I ask you to figure out what current waveform this goes through which of the devices, when the switch is closed, you can see that the current waveform is zero. And when the switch is open, the current waveform mimics that of the inductor. So we have the current waveform being zero, which means no current is going through the element, and then the current is the same as that of the inductor during the second half cycle. And you can see that this waveform is for the diode. Okay, this waveform is for the diode. So the diode is reverse biased in the first half cycle and is forward bias in the second half cycle. This is a constant, and we know that with the assumption we are making, the current through the load is supposed to be constant. So this is IR, and the only element left is the current through the capacitor, and we know that the current through the capacitor using KCL is basically our IL, the current through the inductor, minus the current through the load, which is IR. And when you do that, basically this is the waveform you get, which is basically the waveform of the current through the capacitor. So you need to be able to sketch that going forward for the buck converter and any of the converters we are going to be talking about, even if you don't have them sketched to you, because you know the operation of the converter. Now, the other thing I wanted to add is you should be able to find the average values of these waveforms, all of these waveforms over here. You should be able to also find the RMS values of these waveforms. So you should be able to find first the average values of all the waveforms we have over here, and you should also be able to find the RMS. So that is something you have to work on. Now we are going to go back to take a quick look at our example for today. So over here we have a buck converter. Almost all the elements has been given. So we have Vs, we have the inductor, we have the frequency given. We are operating this DC-DC buck converter at a duty ratio of 0.4. The capacitor has been given to be 100 microfarad, and our resistor is a 20 ohms resistor, purely resistive element. We are being asked to assume ideal components. Okay, so we have been asked to assume ideal components. The first question is to find the output voltage VO. The B part of the question is to find the maximum and the minimum inductor currents, and we know how to do this now. And the last part of the question, if I scroll up, is to be able to find the output voltage ripple. So what is the output voltage ripple? So that's the C part of the question. So we are going to take them one by one. So the first part of the question, we want to find the output voltage. We know that this is a buck converter, and therefore the relationship between the output voltage and the input voltage is given by that. Vs, which is the input voltage, is known. The duty ratio which the converter is going to be operated on is known. Therefore, this is a straightforward question. So the output voltage for this converter is going to be 20 volts, given that the input voltage is 50 volts. The maximum inductor current. The maximum inductor current. So if we have the waveform, we want the maximum and then we want the minimum. Okay. So first we need to find the maximum inductor current. We have an expression for that. So we go and pick out the expression and find out the parameters within the expression that is known and the ones which are not known. If you look at this expression for the maximum inductor current, everything here is known. We just calculated the output voltage VO in the A part of the question. The resistance is known, the D is known, the inductance is known, and the frequency is known. So everything here is known. If you substitute the elements and you do the calculations right, take your time and do that, you are going to come out with a maximum inductor current of 1.75 amps. We apply the same principle to find the minimum inductor current. So we go back to the notes and we get the expression for the minimum inductor current. And you are also going to realize that almost everything here is known. So you go ahead and you substitute the values for that, and you come out with a value of 0.25. This tells us that the buck converter that we are analyzing right now is operating in a CCM mode. Right? The buck converter is operating in a CCM mode, continuous current mode of operation, where the minimum current should be positive. Now, the question could have been, is the buck converter operating in a continuous current mode or not? If that was the question, then what you need to calculate is to calculate IL mean and make sure and check to make sure that IL mean is greater than 0. So that is another type of the question which would have been asked, but then the calculation for that question or the analysis for that question would have been the same, to check to find IL mean and to check to make sure that IL mean is greater than 0. So that is how to find IL mean. The last part of the question is to find the output voltage ripple. Now you could see over here that I've done some side calculations over here. This side calculations is finding the IL average. The IL average is the same as the average current through the load. And the average current through the load, how do we calculate that? The average current through the load is the output voltage, which we calculated earlier, divided by the resistance. When you do that, you get 1 amps. Therefore, the average current which is flowing through the inductor is equal to 1 amps. The change in inductor current, since we know the two peaks, we know if I go up one step, since we've calculated the maximum Imax and we've calculated the minimum inductor current, when we subtract those two, that is going to give us the change in RL. So just in case there is a question where you are supposed to find the change in RL, then this is another procedure, or this is a calculation that you can use to accomplish that. So that was part of my side notes in my lecture notes. The C part of the question is to find the output voltage ripple. So we go back to the notes and find the expression for the output voltage ripple. So if you look very closely, it's not the change in the output voltage, but the question is to find the output voltage ripple, which is basically the change in the output voltage divided by the actual magnitude of the output voltage. So that's the formula that we have from the notes, and you are going to realize that almost every element in this particular formula is known, so it's just going to boil down to substitution. When you substitute all the elements and you do the calculation right, you are going to come out with this answer, which is the same as 0.46%. So the voltage ripple as a percentage of the actual average voltage across the load is basically less than 0.5%, basically less than, which is a very, very small quantity. So this is basically a quick shot of an example of the buck converter. A different type of questions can be asked. Within this same question, I can ask, or you can be asked, to find the average current across all the elements: the source, the switch, the inductor, the diode, the capacitor, and the load. And just before we started this example, we looked at all the waveforms for the buck converter for each of these elements. So you should be able to find the average current for these elements, and you should also be able to find the RMS currents of these elements. But this is a snapshot of an example of the buck converter that we have looked at in these various sessions. Thank you very much, and this is going to be the end for our buck converter series.